So we're given a linear transformation from R3 to R2. And we're asked to compute a basis for the kernel of T and create a basis for the image of T. Now, you can go through and verify for yourself that this is in fact a linear transformation, which is a good exercise. And in videos later this week, we're going to be doing a lot of confirm this is a linear transformation, and then we'll create a basis and so on and so forth. But we're going to look at creating a basis for the kernel of T and create a basis for the image of T right now. And the nice thing here is that we can use the standard basis. We have to pick a basis. We can use a standard basis, and we have a technique that we're going to use every single time to compute a basis for the kernel of T and compute a basis for the image of T. And it requires us to look at what happens to T of V1, T of V2, and T of V3, where V1, V2, and V3 are the vectors in our basis for V, but we get to pick the basis for V. So I'm going to pick the standard basis. I'm going to look at what happens to 1, 0, 0, T of 0, 1, 0, and T of 0, 0, 1. Now, 1, 0, 0 gets mapped to 3, 2. 0, 1, 0 gets mapped to 2, 1. And 0, 0, 1 gets mapped to -1, 1. Now, I'm going to represent the outputs. I pick the basis, standard basis for W. For V, for W, I'm also going to pick the standard basis. So this is going to be 3E1 plus 2E2. This is going to be 2E1 plus 1E2. This is going to be -1E1 plus 1E2. So this gives me that T, E1, E2, E3, represented using E1, E2, is equal to 3, 2, 2, 1, -1, 1. That gives me my matrix representation. Now, to calculate the kernel, what we're going to do is we're going to take a linear combination A with the 3, 1 plus B 2, 1 plus C -1, 1 equals the 0 vector. And this is TV1 represented in beta, TV2 represented in beta, and TV3 represented in beta. And it creates the homogeneous system of equations 3, 1, 2, 1, -1, 1, 0, 0. And we would like to know when this is 0, what the solution to this is. So to create a basis for our null space, we're actually solving this system of equations. So I'm going to take row 1, swap with row 3 to give me 1, 1, 1, 0, 3, 2, -1, 0. Then I'm going to take row 2. Oh, I swapped with row 2, not row 3. Row 2 -3, row 1, placing row 2 to give me 1, 1, 1, 0, 0, -1, -4, 0. Now, -1, row 2 replaces row 2, 1. Oh, jumping ahead of myself. 1, 1, 1, 0, 0, 1, 4, 0. Now row 1 minus row 2, placing row 1 gives 1, 0, minus 3, 0, 0, 1, 4, 0. Oh, now we're gonna move part B down. Now this gives me the equivalent system of equations. A minus 3C equals 0, and B plus 4C equals 0. And our solution vector is A, B, C. We're going to let C equal T, which is an element of the reals, because C is our free variable. A and B are my basic variables, and C is my free variable. This gives A equals minus 3T, and B equals minus 4T. So A, B, C equals the span, or ABC equals 3T minus 4T, T, which equals T times 3 minus 4, 1, or the vector A, B, C equals the span of the vector 3 minus 4, 1. So that's the solution to this system of equations. Now, if I want to convert this into kernel of T, I have to write what this vector here represents in terms of my original basis. So it's 3 times V1 plus negative 4 times V2 plus 1 times V3, which is equal to 3 times 1, 0, 0, plus minus 4 times 0, 0, 1, plus 1 times, or 0, 1, 0, plus 1 times 0, 0, 1, which is equal to 3 minus 4, 1. Now, while they're the same, it's because I used the standard basis. If a different basis is used, this must change. But this means that the kernel of T is equal to the span of the set containing the vector 3 minus 4, 1. And that's the kernel. So the dimension of the kernel which is equal to the nullity of T is equal to